over here, I have three matrices and three operations that I want you to try and perform on these matrices. So go ahead, pause the video, see if you can do these three operations on your own, and come back here to either check your solution or see how to perform these operations in the first place if you don't know how to. So go ahead and do that and come back to this video.
So before watching this video, you should know that I plan to make videos covering the entire undergraduate linear algebra curriculum. So make sure that you subscribe to my channel and turn notifications on, and you'll know when I post a new video that will correspond with the concepts you're covering in class. Also, I plan on making review videos that cover these topics at a faster pace. Check my channel if I've released those already, because that will be useful to you if you already know this concept and you don't have to sit around with a more in-depth explanation, and you should get the content across faster. Okay, cool. With that, let's get back into the video.
Okay, so before we do these matrix operations, the first thing that I want to do is just write out the size of each matrix and how we can describe an individual entry in a matrix. So let's start with the size. Over here, we'll have two rows and two columns. So this would be row 1, row 2. This would be column 1 and column 2. So since we have two rows and two columns, this is a 2 by 2 matrix where the rows come first, the number of rows come first, and then the number of columns. So that's the same here. We have two rows and two columns, so this would also be a 2 by 2 matrix. And over here, this would be, well, we have two rows, this is row 1 and row 2, and we have three columns, this is column 1, column 2, and column 3. So since it's number of rows by number of columns, this would be a 2 by 3 matrix. Since there's two rows, row 1, row 2, and three columns, column 1, column 2, column 3. Now we can go ahead and see how we can describe individual entries in a matrix. So when describing matrices, we usually use uppercase letters like uppercase A, uppercase B, and uppercase C here. Because of my handwriting, this might not look like an uppercase C, but it is, trust me. So here, when we're describing entries, we use lowercase letters. For example, to describe this entry right here, we would use a lowercase letter A first, because that's the lowercase version of the letter that describes the matrix, and then describe the position of the entry using rows and columns. So since it's always rows by columns, this entry right here is in the first row and first column, so it would be 1, 1. To show it's an entry, we would put square brackets around that, and that would just equal 1 because the entry in the first row, first column is 1. A nice way to remember that it's always rows by columns and not column by row is that rows are horizontal, columns are vertical. When we're dealing with a coordinate system, similarly, the horizontal entries come before the vertical entries. For example, x comma y. So here, just like a coordinate system, the horizontal rows come before the vertical columns. I don't know if that's how the convention came to be, but that's just the way that I like to remember it. And we can describe this 2 over here, for example, by stating the row that it's in and then the column that it's in. So this is row 1, row 2, so this 2 is in row 2, and this is in column, well, not column 1, column 2, but column 3. So we count from left to right and up to down when naming rows and columns. So row 2, column 3, so once again, this would be a lowercase c, because the matrix itself is uppercase C, and the entry is in row 2, column 3, so we could write 2 because row come first, then 3 because column 3, and then put square brackets around it and say that it's equal to 2. Okay, so now that we have the convention for writing entries in a matrix and the size of the matrices, let's go ahead and apply some operations. Here, we can add matrix A to matrix B by adding every single term in matrix A to its corresponding term in matrix B. Let me show you an example. Here, if we had to add 1 to something matrix B, we would add it to 0, because that's the corresponding term in B. Since A is in the position 1, 1, we also have to add that to this entry in a position 1, 1 in matrix B as well, so in this case 0. So I would say 1 plus 0, which is 1, we would keep it in the same position because that's the position that it came from. We have to add the 2 to a 1 because that's the entry in the same position as the 2 in matrix A. So 2 plus 1 is 3. 3 plus 1 would be 4. And 4 plus 2 would be 6, because all we're really doing is taking all of the entries in their respective positions in matrix A and adding those entries to the entries in matrix B in that same position. So matrix addition isn't that complicated. All you have to do is just look at the position in one matrix and add it to the entry in that position in the other matrix, and you should be good. You can't always do matrix addition. For example, we can't add A to C because they're different sizes. So there's entries in C that have no corresponding entries in A. For example, this 3 and this 2 don't have a corresponding entry in A. So you technically can't add matrix A to matrix C. That's impossible. So just be careful that when you're adding matrices, you make sure you're adding matrices of the same size. Another operation that you can do is you can multiply a matrix by a scalar constant. For example, here we're multiplying matrix B by the constant -2. In fact, we can rewrite this operation as A plus -2, a constant, times the matrix B. To multiply a matrix by a scalar constant, all you have to do is just multiply every single term in matrix B by the scalar constant -2. So -2 times 0 would equal 0. All we're doing is just taking every single term in matrix B and multiplying it by -2. So this would be 0. -2 times 1 is -2. -2 times 1 is once again -2. -2 times 2 is -4. So that's -2 times B. And we can add that to matrix A, which is 1, 2, 3, 4. And when we add these two matrices, we will get, once again, we just have to take all the terms in A and add them to their corresponding terms in the same position in B. So 1 plus 0 would be 1. 2 minus 2 is 0. 3 minus 2 is 1. 4 minus 4 is 0. I just took the entries in matrix A and added them to their corresponding entries in B, and I got this matrix. This matrix is the result of applying this operation right here. Cool. So that's matrix addition and multiplying a matrix by a scalar constant. I might have gone a little fast there, but really these aren't the operations that students are usually tricked by. They're somewhat simple because all you have to do for adding matrices is just adding all the corresponding terms in A to the corresponding terms in B. And here, all you really had to do was multiply every single term by the scalar constant in order to multiply a matrix by a scalar constant. So that shouldn't be too difficult. So let's move on to C. Here, when we're multiplying two matrices, this is the one that's usually the most tricky for students because it's the most involved. But it's not that bad, and hopefully I'll be able to simplify it for you. The first thing that you really want to do when you're doing this is making sure it's possible in the first place, because there's cases where you can multiply two matrices. When you're adding two matrices, it'll be pretty easy to see if it's impossible because, well, they have to be of the same size. If they're not, you're done. But for matrix multiplication, it's once again a little bit more involved. So let me show you how you could see if they're possible. To see if it's possible, just check that the number of columns in the first matrix in the multiplication is equal to the number of rows in the second matrix. So here I'm taking a 2 by 2 matrix and I am multiplying it by a 3 by 2 matrix. Or sorry, a 2 by 3 matrix, my bad. So since we're multiplying a 2 by 2 by a 2 by 3, we can actually do this because the number of rows in the 2 by 2 or the number of columns in the 2 by 2 matrix, or the first matrix, is equal to the number of rows in the 2 by 3 matrix. The number of columns in the first matrix is equal to the number of rows in the second matrix. However, if we're doing C times A, let's go ahead and write that out, we would have 2 by 3 times, well, 2 by 2 because A is 2 by 2, and the number of columns here don't equal the number of columns here, so this wouldn't even be possible. We can only multiply two matrices if the number of columns of the first matrix equal the number of rows in the second matrix. Here, since the number of columns in matrix A equals the number of rows in matrix C, we can go ahead and apply matrix multiplication. Hopefully that makes sense. Okay, so now let's go ahead and move on to how we multiply these two matrices. So the way that we do this is, well, the first thing is let me just rewrite these matrices here so it'll be a little bit easier to see. But basically, we're just going to take every single entry in the row of the first matrix and multiply it by every single entry in the column of the second matrix, add them up, and that'll create a new entry in the matrix resulting from this operation. That might have sounded super complicated, but that's just the gist of it, and it'll be really simple once I show you with this example. Okay, so remember, it's always rows multiplied by columns. It's always rows by columns. That's all you need to remember for like all of the memorization here. It's always rows by columns, and here in matrix multiplication, it's once again rows by columns. So let's go ahead and let's start by multiplying this row here, row 1, by column 1 in this matrix. You're always going to deal with columns in the second matrix, and you're always going to deal with rows in the first matrix because it's always rows by columns. So we multiplied row 1 by column 1. So doing that, we take every single entry in row 1 and multiply it by the corresponding entry in column 1. So this is entry 1 in row 1, so we need to multiply it by entry 1 in column 1. So 1 times 1 would equal 1. And then we need to add that to the second entry in row 1 multiplied by the second entry in column 1. So 2 times 2 is 4. So here 1 plus 4 is equal to 5. So this is one of our entries in the new matrix. I'll reiterate because that was very important, and that's basically what we're going to do for every single entry in our new matrix. We multiplied row 1 by column 1, and we took every single entry in row 1 and multiplied by every single entry in column 1, and we added them together, and that gave us an entry in our new matrix. So now the question is, which entry is this? Well, if we multiply row 1 by column 1, then it's going to be entry 1, 1. If we multiplied row 1 by column 2, then it's going to be entry 1, 2, and so on. So here we got entry 1, 1. Now we can go ahead and do this for every other entry in this matrix. So let's go ahead and do that. We can multiply row 1 by column 2, so 1, 2 times 0, negative 1. So 1 times 0 is 0. 2 times negative 1 is negative 2. So 0 minus 2 will give us minus 2. And that's row 1 times column 2. So this would give us the entry in 1, 2. So negative 2 would go right here. Finally, for the last entry in this row, we could do row 1 times column 3. So 1 times 3 times plus 2 times 2. So 1 plus 3 is 3, and 2 times 2 is 4. So 3 plus 4 is 7, will give us the last entry in this row. And now we could go ahead and move on to the second row. This row right here. So here we would do 3 times 1 because we need to find the entry in row 2, column 1. So 3 times 1 is 1. And 4 times 2 is 8. So 3 times 1 is 3. And 4 times 2 is 8. So 8 plus 3 is 11. Is 8. Now we can go ahead and do this for this column. So row 1 times column 2, 3 times 0 is 0, 4 times minus 1 is minus 4, so 0 minus 4 is just minus 4. And finally, we can do this for the last column. So 3 times 3 is 9, 4 times 2 is 8, 9 plus 8 is 17. So that would be row 2 times column 3, and that would give us the entry 2, 3 in our new matrix. So 3 times 3 is 9, 4 times 2 is 8, so 9 plus 8 is 17, and we're done. This is the resulting matrix from matrix multiplication. Now, before I go, I just want to do one last thing, which is show that how we could have determined the size of this matrix without even doing the multiplication. So this right here was, well, we have 2 rows and 3 columns. This would be a 2 by 3 matrix. And the way that we could have figured out that this was a 2 by 3 matrix is if we saw over here, well, we're going to use these 2's for the matrix multiplication because they're the same number. We can cross them out. This is just a shortcut. So the resulting matrix is going to be 2 by 3. Once again, that's just a shortcut. You could see how it worked out to be a 2 by 3. But if we cross out the columns from the first matrix and the rows of the second matrix, then we're left with rows by columns, and that's going to be the size of a resulting matrix. Hopefully that makes sense. It's a bit of an unorthodox trick, but that's just how I like to think about it before even doing the matrix multiplication. We can figure out that this matrix is 2 by 3. So hopefully that gave you a little bit of insight into how you can perform matrix multiplication and all of these operations and how you can do matrix algebra in the first place.
I just wanted to thank you for sticking around until the end of the video. It really does mean a lot to me. If you have any questions, you're welcome to leave a comment, and I'll try and respond as quickly as possible. On screen, you should see a link to a playlist containing every single one of my individual linear algebra videos that I made so far, and the ones that I would have made in the future, so go ahead and check that out. You should also see my last video, so if you're a little bit confused in this one and want to see the previous concept, you can click on that. And finally, you should see a subscribe button, and if you want to be notified for my future videos, and also wanted to tell me that you enjoyed this video, you can do that. Okay, cool. So that's it, and until next time, bye!